Yes, hello everyone. Is this audible?
Yes, ma'am. Good evening.
No, good evening. All right, so we had started with the second chapter of your first unit electrostatics, that is electric potential and capacitance. No, so we had studied what is meant by electric potential. So, according to the definition of electric potential is basically the work done to move a unit positive test charge from infinity to a particular point. So, what was the formula of potential due to a point charge? Yes. Yes, Krishna.
It's KQ by R.
KQ by R. It is only KQ by R. Now, see, we had started with a question, but we couldn't complete it. So let's do these two parts left. Did anyone try what is the potential at point E and work done? If anybody has tried and has got the answer, just write me in the chat box. I'll see and I'll let you know whether it's correct or not. Otherwise, let's continue with the second and the third part. Now, see, in the first part, we had to find out the potential at the center point O. In this, what happened? All the potentials got cancelled because K E by A by root 2 minus K by root 2 got cancelled. 2Ke by A by root 2 minus 2Ke by root 2 got cancelled. So it became 0. Now, in this second part, we have this point E, which is situated in the middle of BC. It means it is dividing this A into two parts, A by 2, A by 2. Now we have to find out the potential at this point. So potential will of course be generated by plus E, minus E, plus 2E, minus 2E, all these charges only. Now see, if these charges are generating, we have to find out the separation. Like we had to find out the potential at point O. We first did what? We first took out what's the separation of it. So it came out to be A by root 2. So we understood that this separation is A by root 2. That's why we utilized A by root 2 everywhere. Now it means we have to find out all the charges separation to this point E. So if you consider the first charge, AE, this is unknown. It means we first have to find out what is AE. Then to this charge minus E, we know it's A by 2. With C also it's A by 2. Again, with DE, it is unknown. So it means the task is to find out AE. AE or DE, both are equal. Now see if you're able to observe, this is again a right angle triangle. This side is A, this is A by 2. By using Pythagoras Theorem, we'll be able to find out the hypotenuse, means AE. And if you know AE and DE, both are equal. Both of them are meeting at this point D. Just error in the figure. Otherwise, both of these points are meeting at this point D, minus 2 charge. So if we find out AE, means second part, AE will be equal to what? One side was A, so it will be A square. Other side was A by 2, means BE was what? A by 2. So this becomes A square by 4 under root. This is your Pythagoras theorem. What was our triangle? This was A point, this was E point, this was B point. AB is the side of the square, so it will be A. BC side has been divided into two equal parts by the point E. So this becomes A by 2. Now you have to find this. So this will definitely be A square plus A square by 4. So that's what we are finding out. So this will be 4A square plus A square means 5A square by 4 under root. Now A square by 4 under root means A by 2 only. So this becomes A root 5, within the root is 5 and 2, because A square by 4 under root will be A by 2. This is AE, which is also equal to DE. This was the only missing quantity. Now we'll be able to solve the question. So VE at this point, E point, first let us find out what is the potential. Again, like I've told you previously, how you have to calculate the potential using this formula only. We had found the potential at point O using this same formula. Now see, V is equal to KQ by R. K is the constant, so for point E due to A, K will remain the same. Now Q, regarding the charge at point A is plus E. So you have KE with you divided by R. R is what? R is the separation between the point and the charge. That is AE, and AE we have just calculated, that is A root 5 by 2. So instead of R, we'll have A root 5 by 2. This is how we'll write. Since charge plus E is over here, dA will be what? K. Instead of Q, that is the charge, we have plus E divided by the separation of the point to the charge. This distance, what is this distance? A root 5 by 2. This is VA, how you have to calculate VA. Now VB. VB has this point. VB has minus E. So see, you have the constant K with you. K Q by R. Q, what is the charge at B? Minus E. So we have to consider minus E sign. Why are we considering this minus sign?
Because potential is a scalar.
Correct. Because potential is a scalar quantity, so that's why we are considering this minus sign. Divided by. Okay, Atif, tell me what is R that I should take?
A by 2.
A by 2, correct. The separation of the charge from the point is A by 2. So this will be A by 2. Then VC means the other half. This portion for C and D, this is plus 2E minus 2. Let me draw it again over here. For VC, this is point C, this is point D, this is point E. So DE is also A root 5 by 2. EC is A by 2. DC is A. These are all the sides given. C has minus 2E and D has plus 2E. Or is it the opposite? Okay, C has plus 2E and D has negative 2E. This is minus 2E. Now we have to find out what is the potential at point C. Yes, Fatima, what is the potential at point C? Dictate it to me. Yes, Fatima?
K times 2E divided by A by 2.
Divided by A by 2, correct. Divided by A by 2. Because the separation of the charge to this point, this is A by 2. Good. So A, B, C we have. Last final potential is for point D. Josefa, what will be the potential for point D? This is your D point. This is the charge. This is E point at which we are calculating the potential. Separation of D and E is root 5 A by 2. Yes, Josefa, try. Yes, Josefa? Josefa, are you able to hear? Okay, Josefa. So unmute yourself, just try. I'll help you out. In the general formula for it is KQ by R. The general formula is KQ by R. So if you have it as KQ by R, so you have to identify the charge, you have to identify the separation. Yes, Josefa. Charge is minus 2e. Charge is definitely minus 2e. So it will be K. Instead of writing the charge, I have it as minus 2e. Separation, R. What will be R? R is A root 5 by 2, correct. R will be A root 5 by 2. Because we have this distance, this is the charge minus 2e. This is the point at which we are calculating. And the separation is this. Now we have to find out the net potential. Net potential will be what? Sum of all the potentials means Ke divided by A root 5 by 2. Then VB minus Ke A by 2. VC plus K2E A by 2. Then we have minus K2E A by A root 5 by 2. This is A root 5 by 2. This is your net potential. That's how you have to calculate the net potential. Once you have all the values for potential, what did we do? We first took the general formula for potential is KQ by R. So you have K with you, the constant, that will remain same. You have to see which charge is contributing. Then the separation or the distance that you are considering. That gives you the net potential. Once you have the net potential, then you will be easily able to calculate the net answer. Now see, V net you have. So in this you can do one thing. You can take out KE common, KE by A at least you can take common. C2 KE by A. Yes, this is common from every part. Just look at it. 2 will go up. So 2 KE we have taken. From here, what is left? 2 KE we have taken. From here, 1 by root 5 is left. From here, 2 KE by whole completely we have taken it. So this will be minus 1. Now, from this part we have 2 KE by A as common. So this will be plus 2 because 1, 2 we have taken. And from here, 2 KE by A we have taken common. So minus 2 by root 5, this will be left. This will be what will be left. So V net will be what? This will be 2 KE by A.
Ma'am, it will be minus 4 by root 5.
From here,
Because
2 we have taken common.
Okay.
Okay, so this will be 1 by root 5. We have just taken common. You can simplify the way you have to. It's just that you won't get a single answer because E charge value you have to put. So you will get it in terms of root only. Do one thing, take whatever things are common. You can take minus 2 KE by A common as per your wish. So ultimately, when you simplify it, you will be left with this much only. Now see, the last part that it was saying, it has asked you to calculate the work done. The third part, I believe this was asking you work done in carrying proton from point O to point E. Now, you know the potential at point O. What was the potential at point O? 0 at the center. We calculated on Tuesday. And right now, V net at this is what? V net means VE, potential at E point. This is it. So work done is what? Work done is charge of a proton means electronic charge. E is the electronic charge, the charge for proton, multiplied by VE minus VO. Since VO is 0, you just multiply it with it. If you multiply it with, if you get work done as E, VE is what? 2 KEA, 1 minus 1 by root 5. minus VO. VO is 0. So work done will simply be, you can directly square it and write it. This will be 2ke square by A, 1 minus 1 by root 5. All right, because this EE gets multiplied. That's how you will be solving. So what's your task? See, there's a set pattern. You have to find out potential for each point, add it, subtract it by whatever sign is there, means using basic algebra, just add or subtract it. If you are given work done, take the final potential, subtract it from the initial potential to get the potential difference, multiply it with the charge that you are provided, you'll get the work done as well. Clear to all of you?
Yes, ma'am.
Okay, so just note down the solution for second and third part.
Teacher, I joined late, so can I write the first one also?
First part, Fatima, we did on Tuesday only, no? At the center 0. I think you have written it.
Yeah, I did it.
Okay.
Thank you.
Done?
Yes.
Oh. Now see, that was about electric potentials introduction. Now we'll do potential that is generated because of a dipole. If you have a dipole, then what is the potential? See, potential for a point charge we did, that was kq by r. Now if you have a dipole, if you remember, it is a set of two charges which are equal in magnitude but opposite in sign. Means if one is positive, other one will be negative. Let's say both of these dipole, both of these charges are separated by 2a. Now, I'm not considering any axial point, I'm not considering any equatorial point, I'm taking a random point P point. This is neither axial nor equatorial, just a random point I have taken. Let's take the separation of this point from both the charges. So this is separation of Q1 and Q2 is separated in this manner. So let's say this is R1 and let's say this is R2. Now, if you remember when we were deriving potential in case of electric field one, what did we do? We took a point, we took a separation R. R from where? From the midpoint of the dipole to the point. That's what we took R, no? Where we got our formula as Kp by R cube and whatever electric fields that we got. So in case of potential also, from the center means middle, making this as A, making this as A. Let us take a point. This point, and let's even expand it because that will help us in dropping the perpendiculars. This is R. This is the R that we used to take. Whatever is the point, we have just joined it with the center of the dipole. And since the length of the dipole is 2a, each part becomes a. Now see, let's do some construction. I have dropped perpendicular on this line that I'm getting. Let me name it. Let's say this is A, this is already P, this is B. Let it be that this be C, this is perpendicular drop, and let it be E. This is also another perpendicular. All right, this is O. This is the center of the dipole. Now see, potential at point. If I have to calculate the potential at point P, the general formula of potential will be what? The way we have been calculating, KQ by R. So K, Q is what? Plus Q divided by R. Separation is R1. The other charge is negative, so minus KQ by R2. This is how we calculate. So this is the answer only. But see, R1 and R2, these are not provided to us. No, we only know A and small r. So we have to somehow manage our answer in terms of R1 and R2 so that R1 and R2 gets converted into small r. This is small r and A. So we don't require this R1 and R2. Rest, otherwise your answer is fine till here. You can take KQ common and write it as 1 by R1 minus 1 by R2. But R1 and R2, we have taken it from our own. So we have to simplify it. What is meant by R1, what is meant by R2. Now see, PA and this PC, these are almost equal. PA is almost equal to PC. So if PA and PC are almost equal, because this gap is very small that I've drawn. PC is made up of what? PC is made up of PO and this small OC that is extending. So PA will be what? PO plus this OC. All right. Now, PA is already R1. PO is already small r, but OC is new. We don't know what is OC. So let's take angle. Let's make these two angles as theta, these vertically opposite angles as theta. Now see, if you consider this triangle AOC. Just look at this triangle AOC. This is this triangle drawn. This is theta. This is A point. This is O point. This is C point. This separation is OC. This separation, this is OC, this is small a. You can look, this separation is small a and this is C. Now, if I write what is cos theta in this, cos theta, this will be OC divided by what? OC divided by AO. So from here, I can get the value of OC as well. If OC is AO divided cos theta multiplied by AO. So OC will be what? OC will be AO multiplied by cos theta, means OC is what? AO is small a cos theta. So R1 will be what? R1 is R plus A cos theta. This is the value of R1. But I have one more variable with me, R2. I need to find out what is R2. So similarly, we can do it for PB, that is almost equal to this. We know PB already, no? So if you look at this figure PB, this is almost equal to PO, the shorter one. Both of them, if you look at the figure, these are equal. If you look, these were equal. But if you look at them, PO and PB, both of them are equal. So let us write in this manner only. PO This is almost equal to PB. Now see, PO is made up of what? PB is equal to PO. So let's see, PO is made up of what? PO is, this is PO, not even PO. In fact, PO will be greater. Let's take PD. PD and PB will be much compared. Let's take PD because PO will be a little longer. So let's take PD. PB is almost equal to PD because PB also will be longer. Now see, PD is made up of what? If you take this whole long part PC and extract the CD, what will be left? Only PD will be left. So PB is made up of what? It is made up of PO minus this small segment OD. That will give you PB. We had considered that side, that is already R2. PO is small r, OP or PO is a small r. OD is what? Again, OD is unknown. So if you draw this triangle, okay, let me draw the triangle here. This is the triangle, this is the theta that I'm considering, this D point, this was the center O, and this was what point? This was B point. B point, right? This is B point. So OB is A, and we have to find out OD. Again, if we consider cos theta, because see, we have to eliminate OD. Again, if we consider cos theta, we'll be left with OD divided by small a, this part. This was the perpendicular. So OD will be what? A cos theta. So R2 is R minus A cos theta. So I have the value of R1 and R2 mean. This is the value of R1, R plus A cos theta, and R2 is R minus A cos theta. So in this formula, KQ 1 by R1 minus 1 by R2, I can put the value of R1 and R2 now. So we will be what? We will be KQ. Let KQ be common only. 1 by R plus A cos theta minus 1 by R minus A cos theta. Instead of R1 and R2, I'm writing with the values that we have derived right now. So let's take the LCM because no other option is there. So this will be R minus A cos theta, or let me take the minus sign also common for it. This, because this is negative, and then this will be plus AR plus A cos theta divided by, multiplying both the brackets, R plus A cos theta multiplied by R minus A cos theta. So if I open these brackets, we will be minus R plus A cos theta plus R plus A cos theta. Can any one of you remember which identity is this denominator forming? A plus B, A minus B. This is equal to what?
A square minus B square.
A square minus B square. So this will be R square minus A square cos square theta. And R will also get cancelled. So this will be KQ 2A cos theta. A cos theta will get added, divided by R square minus A square cos square theta. Now Q multiplied by 2A is what?
P.
P, dipole moment. If you remember, dipole was what? Charge multiplied by the separation of them. So potential becomes Kp cos theta divided by R square minus A square cos square theta. This is your potentials formula for dipole. Now anyone, can anyone of you tell me what was ideal dipole approximation that we used? Ideal dipole approximation. What was the approximation in this?
R is much greater than E.
Correct, Atika. The ideal dipole approximation, in this, the approximation that we take is if the size of dipole is very small. As soon as the size of dipole becomes small, the separation of the midpoint to that point means small r, this becomes greater. So under ideal dipole approximation, if you have ideal dipole approximation, then your small r becomes greater than capital, small r becomes very much greater than a, because now a has been reduced, the size of 2a has been reduced. So if you have r square minus a square cos square theta, it's like r square is, if r is 10, a is 1. What are you doing? You are subtracting 100 minus 1, that is almost equal to 99. So instead of writing 99, I can write it as 100 also, approximation. So r square minus a square cos square theta can also be written as r square. So your potential becomes kp cos theta. Instead of this whole term, I'm just writing r square. So this is your potential case. Now see, I have not derived it for axial or equatorial line. This is the general case. What if I have to derive, or I get the point at axial line? If I get the point at the axial line, just think, this is your dipole plus q minus q. This is the point I'm taking, P. This is small r, and this is theta. Now see, in case of axial line, what will happen? I'll bring the point to the axis. If this is the dipole, I'll be inclining it back in this manner. Let's say this was some 60 degrees. Then I'll first put P over here. This angle will become lesser than 60, maybe 30 degrees. Then I'll bring P much closer than the dipole, near to the axis. This will become more close, more lesser than it, 10 degrees. What if I bring the point P over here, means the axis? What will be the angle now?
0
0 degree, correct. Both of you are correct. It will be 0 degrees. So it means we just don't need to derive it for axial and equatorial line if we have done this much. Just put theta as 0 degree. V is equal to Kp, cos 0 is 1. So this will be r square. You already have the formula of axial line with you. Second case was what? Your equatorial line. Now see, just opposite to it. If this is the dipole plus q minus q, and this was point P. Let's say this point was 60 degrees. We had started with 60 degrees. Equatorial point is always lies at the center. Not the center, at perpendicular distance to it. So let us expand this. Let's say this is point P. So it will increase to some 70 degrees. Then again, we have expanded it to it. This point will become greater. This will become 80 degrees. Finally, at this point, what will be the angle?
90 degree.
90 degrees. So it means at equatorial line, your theta becomes 90 degrees. And cos 90 is what?
0.
1
0, 0, 0. Krishna 0. So V becomes 0. So you don't have any potential in case of equatorial line. Is this clear now? Dipole case?
Yes, ma'am.
So just note it down, then we'll do a question that will help you.
Can you scroll up 1 minute? Okay, teacher, you can scroll down. Thank you.
At least note down the question and draw the graph and try to plot these points on the graph. Where will these lie? Where will these charges lie? Where will these 3 points A, B, and C will lie? At least do this much, then we'll discuss. First, note down the question. Two charges plus q minus q are placed at 0, 0, comma minus a and 0, 0 plus a. So see, 0, comma 0 means x-axis is 0, y-axis is 0. You have to place it at z-axis. Let's say this is y-axis, this is x-axis, this is negative z-axis, and this is positive z-axis, this is negative x-axis, and this will be negative y-axis. This is your origin. Now that you have to identify where the charge is located. 0, comma 0, comma minus a means negative z-axis. So the charge is located at negative z-axis. This is your charge plus q, which is located at negative z-axis minus a. It means the magnitude of this means the displacement is a. If you have this point, the separation is a, how will you write this point? You will write this point as 0, comma 0, comma minus a only, because this point of the graph will be some minus a. The other charge minus q, this will be on the positive z-axis. Why? 0, comma 0, comma plus a. So this will be 0, comma 0, comma plus a. It means this is, so this is your dipole on the z-axis. Now the first part is saying calculate potential at a point A, which is 0, comma 0, comma z. You don't even need to locate this point. Without the location of this point, you will get done. You have R as z. This is the axial case now. 0, comma 0, comma z means what? X is 0, y is 0. You have the charge or this point at z-axis. If you have the point at z-axis, it was plus z, no? Yeah, plus z. It means it will be somewhere here on this. Let's say this is point A. So this becomes axial line case. Why? Because the dipole is located on z-axis, and on the same axis we have the point A. Now we know R is z in this case. So this, the answer for the first part will be what? You have R as Z. The general formula of potential is what? General formula of potential is V is equal to Kp cos theta, Kp cos theta divided by R square minus A square cos square theta. This is the general formula. Now see direction of dipole. Yes. Hiba, what is the direction of dipole? From negative charge to positive charge or from positive charge to negative charge? Hiba.
I'm from positive to negative.
From negative to positive. See, this is your negative charge from negative to positive. This will be the direction of the dipole. All right, so this will be the direction of dipole like this, from negative charge to the positive charge. So Kp cos theta, the point. So your angle is directly zero. You can see your point and your this P means dipole is both are coinciding and you have angle as 0 degree in case of axial line. So you will have Kp divided by, instead of R square, we have Z square minus A square. Because cos square is theta and cos theta, this has become 1 only. So you don't need to solve it. So this will be Z square minus A square. This is the potential for the first part. Now you have to locate these 2 points, B point and C point. B point says x comma y comma 0. It means it has some value of x axis. It has some value from y axis. Only z axis is 0. This means it is lying in the xy plane. Let's say this is some point B. It has some value from x axis, that is x. It has some value from this y axis, that is y, and it has no value on the z axis. You can see no value on z axis. So this is 0. That's how you have to identify how to locate a point first. X comma y comma 0 shows that the point lies in the xy plane. Just tell me one thing, any one of you can tell. If your point lies on xy plane, what angle will it be making with the z axis?
90 degrees.
90 degree.
90 degrees. It means this point is now at equatorial. This point acts on the equatorial line for the dipole. You have the xy plane like this. Y axis, x axis. XY plane, this becomes the XY plane. You have Z axis like this coming out of the XY plane. Perpendicular to the XY plane, you have Z axis. Perpendicular to XZ plane, you have Y axis. Perpendicular to ZY plane, you have X axis. So perpendicular to XY plane, you have Z axis. It means B point is at equatorial. So for the answer for the second part, VB, this will be 0. Equatorial line we have studied, because this is the case of equatorial. The third point that it has given us, C point. C point says x comma 0 comma 0, means only value from x axis, no value from z axis or y axis. It means if I say this point, let this point be C, some value on the x axis, no value of y axis, no value of z axis. This is point C. But tell me one thing, what is the angle that z axis and x axis make?
90 degree.
90 degrees. See, all the 3 axes are perpendicular to each other. Y is perpendicular to x, which is perpendicular to z. So whenever I'm drawing like this doesn't mean that this is some 60 degree. This is 90 degree. Just to represent that y axis, x axis is going into your notebook in which you are writing. But just to represent it, we are drawing it slightly tilted. Otherwise, z axis is going into your notebook like this. Y axis is straight. So the angle is what? Angle will remain 90 degree. All the axes, this is 90 degree, this is 90 degree. All the angles, all the axes are perpendicular to each other. So C point is where? C point is on x axis. Dipole is where? Z axis. It means again your angle is 90 degrees. So VC will also be 0 by equatorial. Now the third part. Third part says work done in carrying proton from B to C. Work done. How do we calculate the work done? Work done from B to C means charge multiplied by the change in potential. B to C means VB minus VC. Both are 0, so work done also becomes 0. The fourth part asks us whether work is a conservative or not. You see, electric field is always conservative. Electric field is conservative. So it means work done is path independent. This already we have discussed. This makes work done as path independent. So most importantly, first, second and third part. First and the second part are important, where you have to identify what is the location of the point. Identify the location. If it is axial case, identify. If it is an equatorial case, identify. If it's a general case, then you know the general formula. You might be given any angle so as to put it into cos theta. Clear?
Yes, ma'am.
Okay, so note down the solution. Done?
Yes, sir.
Now, so before we move on to the next topic, there's one small topic, relation between electric field and potential. Relation between electric field and potential. Now see, if I give you electric field lines, these are electric field lines, and I have taken 2 points, A point, B point. These are curves. These curves are what? Electric field lines. This separation AB, this is dr. And how do we get the direction of electric field on electric field lines?
By the tangent.
Correct, by the tangent. So if you drop a tangent, you will get the electric field as well. And let's say the charge present is Q. I'm moving this charge Q from A point to B point. So if I'm moving the charge, work done will be what? Work done is Fs, means force multiplied by displacement. So work done will be what? Force on charge Q due to electric field E. This will be QE. And displacement is what? Dr. This is the displacement. Even if the curve is this AB, displacement is this only, no? Dr. So this will be Dr. For one value of work done that you have. Now, apart from this, using your potential concept, which we have studied, charge is Q, potential difference from point A to point B, the charge is moving. So it will be what? dV, change in potential. So I have 2 values of work done, QEdr and QdV. Now let me equate them. QEdr, QdV. So QQ gets cancelled. Electric field is what? Electric field is dV by dr. This is the relationship of electric field with potential. Just one thing, a negative sign you have to add automatically. And what is the significance of this negative sign? I'll tell you. But before that, remember, electric field is what? Differentiation of potential by the change in the distance. Now, see, if you remember from your 11th standard only, whenever you take the change with respect to time, like velocity is what? Displacement divided by time. So you call it as rate of change of displacement gives you velocity. Whenever anything gets divided by time, we call it as rate. Like we call acceleration as rate of change of velocity. Why? Because it is velocity divided by time. But whenever you have anything divided by position, or anything gets changed with respect to position, like the way potential is getting changed with respect to position, we call it as a gradient. This is this dV by dr, specifically this part. This is change in potential with respect to position, and we call it as a gradient. So whenever by chance if you are asked what is the potential gradient and you are given electric field, so you should be able to identify that it is asking you what is dV by dr. dV by dr is what? It is electric field. Whatever is the question, you can manage. Just remember, this is known as the gradient. So how do you calculate net electric field? Just calculate it for all the 3 axes with you. Like if you have x-axis, Ex will be minus dV by dx. For y-axis, Ey will be minus dV by dy. For z-axis, it will be minus dV by dz. And how do you get the net electric field? Net electric field is given by Ex vector plus Ey vector plus Ez vector. This is how you get electric field. Now see, apart from this, okay, one more thing, negative sign I have not told you, no? What is negative sign? So in your NCRT also, these 2 points are clearly written. One is electric field is the change of potential with respect to distance. That is potential gradient. This was your one main point. The other point is the significance of negative sign. Significance of the negative sign that we have, minus sign that we have. So the significance of this sign, this basically minus dV by dr, this minus sign, this is along the direction. This shows that along the direction of the electric field is where the potential decreases. Electric field and electric potential are directly proportional to each other. From this example or from this formula, we are able to observe this only. Know that electric field is directly proportional to potential. So wherever potential is greatest, electric field should be greatest there. But this minus sign, this shows that this is not the case. Electric field is where potential decreases. So it's along the direction of field where potential decreases. Apart from this, or okay, let me give you an example of this. If you have point A 5 volt, point B as 2 volt, this is point A, point B. These are separated by some distance. Direction of electric field in this case, electric field will be in this manner, moving towards B. Why? Because lesser of the potential is 2 volt than 5 volt. So electric field's direction will be this. This is what is the significance of this negative sign, and you get these 2 points clearly. From this topic, you have the theoretical points as what is the relationship between electric field and the potential, means this formula that electric field is the potential gradient, and the second is the negative sign. Why do we get this negative sign? Apart from this, you also have partial derivation. Like Ex, you have delta V by delta X. For y-axis, you have dV by delta V by delta Y. For z-axis, you have delta V by delta Y, delta Z. But this won't get clear like this. Partial differentiation, I'll give you a question and teach you how do we do partial differentiation, or how do we get partial derivatives of anything. For now, you have to remember first, electric field is what? Change in potential. So it can also be written as delta V minus delta V by delta R also. This can be also relation if it is possible to use it. All right, so this relation you have to remember, E is equal to minus dV by dr, and you have to know the significance of this negative sign. So let's do some questions on it, how to do this, how to use the formula, and then we'll see how to solve the partial differentiation. All right, so quickly copy it down.
teacher, 1 minute, please. Okay, teacher, I'm done. Thank you.
So all of you have completed it?
Yes, sir.
Yes, ma'am.
Well, now see, let's see how to use this. Before doing something easy, let me tell you one thing. Potential was what? Potential was kq divided by x. X, I have taken this distance. What if I want electric field from this? If I ask you to calculate electric field. Now see, you already have a relationship between electric field and this. Electric field is what? Minus dv by dx. Since I've taken x, that's why I'm using x. This is basically displacement, to show displacement. Now see, v is what? Kq by x. Electric field will be minus kq by x. This is the differentiation of it by dx. Now see, what do we need to find out? We need to find out electric field. So kq is already common. We have to differentiate kx. See, this kq will come out. Negative sign will also be there. We have to now differentiate dx by x. So let's bring x to the numerator side. Electric field will be what? If you bring x to the numerator side, this will be what? X to the power minus 1. So this is minus kq x to the power minus 1 dx. Now see, kq x to the power minus 1 not multiplied by dx. This is differentiation. It's here in the denominator. So kq dx, we are differentiating this term. So this is differentiation of this x. Now see, how do we differentiate? That's why we had revised calculus. See, kq is a constant, that will come out. Minus kq is a constant, that will come out. X to the power minus 1. Now quickly revise it. X to the power n. Here your n is minus 1. X to the power n is given by nx to the power n minus 1. So n is what? N is minus 1, x to the power minus 1, minus 1. So this becomes minus 1 gets multiplied. This is minus x to the power minus 1 is minus 2. So minus minus will become plus. This will be kq x to the power minus 2. Now did we get kq by x square? This was the formula of electric field, no? Kq by x square. So see, integration and differentiation, these are inverse operations. So if you want to get potential, you can write electric field as kq by x square and then integrate it. Then you will get potential as kq by x, because the relation between electric field and potential uses differentiation. So by using the reverse operation, that is integration, you can get the potential back. Similarly, if you have potential, by differentiating it, you can get the electric field in this manner. So this proves that this relation is also valid. So quickly note down this. Now I'm giving you a question that you all will try yourself. Differentiate it. Firstly, note this down. Just note it down. Then I'm giving you a question.
Teacher, we can also differentiate using the quotient rule, right?
Yes, Satif?
We can also differentiate using the quotient rule, right, on kq by x.
kq by x. Yes, yes. kq by x. You'll get the same answer.
Okay, teacher.
See, this is a very easy question. You have V is equal to 3x cube. Get electric field differentiated, get electric field. You'll get the electric field in terms of x. Put the value of x as 2. See what's your final answer. Everyone should try this question. This is a very basic question and it utilizes this formula E is equal to minus dV by dr. So try and submit your answers after you have copied this down. Just try it yourselves. Others also submit. Only 3 students have given answer. Atif, Krishna and Hanifa. Kulsum and Akifa have submitted. Others also submit. Rishan, submit. Fatima, Fatima Munir, Hamza, Hiba, Zaid. Okay, Hamza is also given answer. Huzaifa, Kulsum and Zaid. Okay, Kulsum has also submitted her answer. So, all right, I think these answers are enough. So, correct answers have been given by Akifa, Krishna, and Atif. Let's discuss it. See, rest of you, V is given to you. V is 3x cube. Electric field is what? Minus dV by dx. You have to differentiate. 3x cube you have to differentiate with respect to what? Dx. 3x cube. 3 is a constant term that will be already there. That will come out. You have to now differentiate x cube. X to the power n is what? N x to the power n minus 1. N is what? N is 3. X to the power n is 3 minus 1. So this becomes 3. X to the power 3 minus 1 is 2. So electric field comes out to be minus 9x squared. This is your electric field. Now, electric field at x equals to 2. Put x equals to 2. Electric field will be what? Minus 9. 2 square. So 4 multiplied by 9 gives you minus 36 volt per meter or Newton per coulomb. Is it clear now to all of you?
Yes, sir.
All right. So just note down this. Written.
Yes.
Now see, I was telling you, partial differentiation. See, let's do it through the example of a question. Let's say V is x square by z square, and you have to calculate electric field. Now, in case of partial differentiation, you have whatever you are differentiating, others become constant. Like E is what? Ex. Ex will be partial differentiation of V by x dv by dx. So in this case, you will be differentiating V by x. Y and Z will act as a constant to you. It means Ex will be what? Differentiate this. You are differentiating x square y z square. Now see, y and z are constants for you. It means y z square constants. What happened to the constants? Constants come out and get multiplied. So out of this x square y z square, this is a constant now when you are solving it for x-axis. So y z square with a negative sign will already be there. Now you have to differentiate x square. X square will be what? 2x to the power 2 minus 1 becomes 2x only. This is your x-axis. Understood? How do we solve it? Differentiate whatever term you are differentiating. Like if you are differentiating it for x-axis, then only differentiate x square. No need to disturb y and z. Why? Because y z square, this is acting as a constant for you. So the constant term comes out. And x square differentiation derivative is 2x only. Now let's do it for y-axis. Ey will be what? Differentiating it in terms of y-axis, this will be minus delta v by dy. Now you are differentiating y-axis, so x and z will act as constants for you. So what was our number? X square y z square. Now which are constants? You are differentiating y, so x square is a constant, z square is a constant. Minus x square z square will come automatically. Why are we putting this sign? This negative sign is of the formula. So x square z square has come out. Now what is left? Dy over dy is left. Means 1 is left. Understood? X square z square came. You are differentiating dx square y z square by dy. This came. What is left? Dy by dy was left. So this gave you 1. This becomes minus x square z square. Let's take example of z-axis. If you are calculating it for z-axis, Ez, this will be partial differentiation of z of voltage with respect to the z-axis. Partial differentiation of voltage with respect to z-axis. Now you are differentiating z component. So x and y act as constants for you. See, what was our number? X square y z square. X is a constant for you. Y is a constant for you. X is a constant. Y is a constant. This constant term will come out. X square y. What is left now? Z square is left. You are differentiating z square. What is the rule? N z to the power n minus 1. What is n right now? N is 2. So this becomes 2z to the power 2 minus 1. What is 2z to the power 2 minus 1? This is 2z only. This is your answer. If you are required to calculate what is the net electric field. So how do we write net electric field? Ex plus Ey plus Ez. So see, electric field is what? E net will be given by. Ex was minus y square 2xz, no? Minus y z square 2x. Minus y z square. Z square 2x. So I'll put I cap because these are vectors, not scalar quantities like potential. Plus y. Y is what? Minus x square z square. So this is minus x square z square j cap. Ey. Then I have to write it for z-axis. Z-axis it is minus x square y 2z. This term with a k cap. This is electric field for z-axis. This is electric field for y-axis. This is electric field for x-axis. All these negative signs are the signs of the formula. Now, even if you get any kind of question, if it says calculate electric field, net electric field at 1, 1, 1, it means x is equal to 1, y is equal to 1, z is equal to 1. Put it over here. E net will be what? If you put y as 1, z as 1, x as 1, this will be minus 2I cap only. If you put z as 1, x as 1, this will be minus j cap only. If you put x, y, z all as 1, this will be minus 2k cap. This will be the net electric field. And even if the question extends further, if it asks you the magnitude of electric field, then the net electric field is been given by, how do you take out the magnitudes if you are given a vector? Take the coefficients and square it and add them. Take the coefficient, square it and add them. Take the coefficient, square it and add them. So this till here, this question can exceed, and this is how you have to use partial differentiation. So how do we solve partial differentiation? Is it clear to all of you?
Yes, ma'am.
Yes, teacher.
What about others? Fatima, Akifa?
Clear, ma'am.
Teacher, how is the symbol for partial differentiation?
This is delta, this. All right.
Yeah, thank you.
Hamza Shekhani, is it getting clear?
Yes, teacher.
Okay, Hanifa, Kulsum Zaid.
Yes, ma'am.
All right.
Teacher, can you explain the last part? Like the root of minus 2 square, how we got that?
This one.
Yes, teacher, can you explain how we got that?
See, if you have any vector which is written in this form, Cartesian form, this is, we call it as Cartesian form. Vectors can be written in polar form as well as in Cartesian form. So if you have vectors written in Cartesian form and you are required to calculate the magnitude, then the general formula says if your vector is a1 I cap plus a2 j cap plus a3 k cap, you have to find out the resultant's magnitude. Then take the coefficient, means a1, whatever is the coefficient. If it is minus a1, take it as minus a1. Square it plus, take now a2, square it, then a3, square it with an under root sign. This gives you the magnitude of a vector. Is this clear now?
Yes, teacher, clear.
Done? Rest of you?
Yes, teacher.
Okay. So the last topic for today is equipotential surface. This is a very easy topic. You just have to remember what is meant by equipotential surfaces, how to draw them. So that I'll help you. Equipotential surfaces, from the term only you can figure out. Equipotential means equal potential. So these are surfaces that have same potential at every point. Same potential at every point. So if let's say I have this sphere with me, the radius of the sphere is r, the whole charge present on the sphere is q. I have taken this point A, the voltage is here 2 volt. I have taken this point B, again the potential is 2 volt. I have taken this point C, again the potential is 2 volt. It means the potential on the whole sphere is 2 volt, whichever point you consider. This means this is an equipotential surface. So there is nothing tough in it. And it doesn't not need to be a sphere only. You can take any random figure which is unequal. If the potential VA is equal to VB is equal to VC, all are same, you can call this as an equipotential surfaces. So some properties equipotential surfaces need to abide by. First property. So see, first property is that the definition only. First property means equipotential surfaces should have same potential. So surfaces having every point with same potential. This is the first condition. Like if you have any random surface with you, you have taken n number of points. You see VA is equal to VB is equal to VC is equal to VD. You can call this surface as an equipotential surface. All right, this is the first property of it. Now see, apart from this, if potential difference doesn't exist, it means VA is equal to VB. If I move a charge from here to here, potential at B was also something, potential at A was also the same value. It means how do we calculate work done? We calculate work done as change in potential. There is no change in potential, means delta V is 0. Why? Because V is constant. Since potential is constant, the change is 0. So work done will be yes, what will be the work done?
0.
0. Work done will also be 0. Charge multiplied by 0, that gives you 0. So if you have equipotential surface, you don't need to calculate anything. Work done will directly be 0. One other property is that if you have a random surface, this is an equipotential surface. I have told you that this is an equipotential surface. So electric field, direction of electric field, remember that it will be always perpendicular to it. Electric field will always be perpendicular. Electric field is perpendicular to equipotential surface. This is another property of it. Apart from this, when we had done electric field lines also, we had drawn this. When field lines are kept together, that shows that strength is high. Similarly, if you have equipotential surfaces aligned closer together in this manner, and then you have equipotential surfaces far apart from each other. This is region 1, this is region 2. So if electric field lines are strong, then equipotential surfaces are closer. If you have equipotential surfaces kept at a distance, that shows it is weak. Weak electric field. Electric field is strong. Electric field is weak. That shows surfaces are far apart from each other. So by looking at the equipotential surfaces, you can directly conclude. So these are the 4 properties of equipotential surface. Now see, if you are given to draw it, like if you are given an isolated charge, Q, isolated charge, how to draw equipotential surfaces? Just keep on drawing concentric circles around this. These represent the equipotential surfaces for a positive point charge. Now see, this is a single charge. What if I take 2 charges? Instead of taking only plus Q, if I take 2 charges, plus Q and plus Q. So will these charges repel each other or attract each other? Repel each other. So it means electric equipotential surfaces. If these are equipotential surfaces, then they will be nearer over here, means where the charge is not present, and will be far away at this point. Nearer here, these are not coinciding. Just draw it properly. They should not coincide. And far away from here because of repulsion. This is close. Here it gets far apart. Here it is close. Here it gets far apart. Now see, this is 2 like charges. So if it is a negative charge, draw it in same manner. 2 unlike charge. Sorry, not unlike, 2 like charges. If you have unlike charges with you, a positive and a negative, 2 like charges. If you have positive and negative charges, it means it is what? It's a dipole. So let me write dipole only instead of writing a positive and negative charge. Definition of dipole, it will be clear. So it means a plus Q you have and a minus Q you have. Now the opposite to what the like charges happen. Equipotential surfaces will now be near here and will be far away from here. This will be near here and far away from here. Then again near to this point where the charges are attracting them and far away from here. Near where charges are here and then far away from here. This is how you draw a dipole. Now see, apart from drawing these charges, you can get to draw electric field. So if you have electric field, uniform electric field. For uniform electric field, what you can do, let's say uniform electric field is associated in which? X-axis. So you can draw these equipotential surfaces at a constant separation, like in this manner. at a constant separation. In this manner, this will be electric field and these will be the equipotential surfaces. But if your electric field is non-uniform, your electric field is non-uniform, non-uniform electric field. So electric field is directed over here only. Electric field is non-uniform. Equipotential surfaces will be drawn how? Wherever fields are closer, let's say electric field is closer in this region. So as we have studied the property, so you have to do application of the properties what you have studied. Equipotential surfaces will be near and equipotential surfaces will be at a certain distance where electric field is weak. This is how you draw equipotential surfaces, by just application of the property. This is a very easy topic. You just have to identify where equipotential surface exists. Wherever you see equal potential is there, constant potential is there, that means that is the equipotential surface. So surfaces that have the same potential. In this case also, potential will be what? KQ by R. Q is the total charge on the sphere. R radius will be the same from here if you take, from here if you take. That's why at every point in the sphere, you get the same potential. So a sphere acts as an equipotential surface if you have uniform charge distribution. All right. And whenever you have to draw, you have to keep these properties in mind, these 4 properties, and you have to draw it like this. Isolated charge, 2 like charges, 2 unlike charges, and how to draw uniform and non-uniform. For uniform, you have to keep it aligned at a certain distance. For non-uniform, you have to keep it separated. Clear to all of you? This is the whole equipotential surface. All right. So just note it down. Yes, done.
Ma'am, can you
teacher.
show the dipole again?
Yes, the dipole one.
Yes, ma'am.
All right.
Thank you, ma'am.
Rest of the part is done. Kulsum.
Yes, ma'am.
All right. What about others? Have you all completed?
Yes, teacher.
Yes, ma'am.
All right. So that's it for today. That completes your equipotential surfaces as well. So we'll continue on Tuesday now. Okay.